Welcome to lecture 44 on essentials of topology. In this lecture 2, we will continue the study of the concept of path connectedness. Specifically, we will see the possible relationship between the concept of connectedness and path connectedness. Begin with what we noted down in the previous lecture, that path connectedness implies connectedness, while connectedness does not imply path connectedness. Let us see the justification of both the statement. Beginning with the first one, that every path connected topological space is connected. In order to justify it, let us take a topological space x tau and assume that this is path connected. Our motive is to justify that this space is connected to. So what we have to justify that this space is connected. This we have to show and this we have assumed. Now let us try to justify by using contradiction. If possible, let us take this space be disconnected. So we are assuming that this x tau is disconnected, and if it is disconnected, what will happen? There exist some subsets a and b of x such that both are non-empty. These a and b are open in x, so these a and b are open in this topological space, that is x tau. We also know that they will always be disjoint and their union is nothing but x. It is to be noted here that a and b are non-empty, so what we can do that we can take some of the elements in these. So let us take x in a and also let us take y in b. So we are assuming it. It means that x and y are elements of x. But at the same time, because this is space x tau which is path connected, what will happen? We can talk about path from x to y, that is, because this space is path connected, there exists a continuous function. This continuous function p from closed interval 0 1 to x such that the value of p0 is x and the value of p at 1 is y. Now, if p0 is x and p1 is y, what we can do that, as x belongs to a, so this p inverse x, this will be an element of p inverse a. Similarly, as y is in b, so p inverse y is an element of p inverse p. It is to be noted, because this p is a continuous function, what we can deduce from here, this p inverse a and p inverse b are non-empty. Second thing, this p inverse a and p inverse b are open in this subspace, that is closed interval 0 1. Also, this A intersection B is an empty set. Therefore, if we are computing P inverse of this intersection, that is P inverse A intersection P inverse B, that is also an empty set. And finally, P inverse A union B is nothing but P inverse X. From here, we can conclude that P inverse A union P inverse B is nothing but closed interval 0. So, if we are assuming that this space is disconnected and it is having a separation that is given by a pair AB, by using this separation, we have constructed a separation, and that is this pair P inverse A and P inverse B, and this is separation of this closed interval 0. Note that this interval is always connected. So what we have got? We reach to a contradiction. Therefore, our assumption which we have taken, that is this space is disconnected, this is wrong. So this space is also connected, that is every path connected topological space is connected. Moving ahead, and let us see the justification of this statement that a connected topological space may not be path connected. In order to justify this statement, it is sufficient to provide a counterexample. It is to be noted that there are no trivial examples for it. What we are going to take here, that is known as topologist sine curve. We will justify that this space is connected, but the same space is not path connected. What the structure is precisely? Let us take a set S, which is collection of this ordered pair, that is x sine 1 upon x. X is greater than 0 and less than or equal to 1. So we are taking this S. Note that this is a subset of R2. So we can talk about the relative topology on S with respect to Euclidean topology on R2. Also, if we are computing the closure of this set, the closure is given by this set itself, and this is x greater than 0 less than or equal to 1 union, this is ordered pair 0 y, where minus 1 is less than or equal to y less than or equal to 1. This curve, that is this set, is known as topologist sine curve. The graph of this curve is given here, that is here we have restricted only x from this point 0 to point 2 only, and the curve looks like in this way, that is this portion is S and the closure of this set, that is this line. It is to be noted that this set S is connected. In order to justify the connectedness of S, let us see it. Let us define a function f from this interval, that is semi-open interval 0 1 to R2. The function is defined like f of x is equal to this x sine 1 upon x. It is to be noted that if we are taking a function something like f1x is equal to x and f2x is equal to sine 1 upon x, domain is our this interval, then both the functions are continuous. Therefore, this f is continuous too. Also, what is the image of this set? That is nothing but f of this interval, that is the semi-open interval, is nothing but S, that is this S is continuous image of a connected space, and therefore this S is also connected. From this S, we are going to construct a set that is not precisely this closure of S. We are going to construct a different set, and we will show that that set is connected to, but that is not path connected. Now, coming to our construction, what we have shown that the set S, which was given as collection of all ordered pairs x sin 1 upon x, where 0 is less than x less than or equal to 1, we have shown that this is connected. We also know that if S is connected, its closure is also connected. And not only its closure, if we are taking any set lying in between S and S closure, that will also be connected. So what we are going to take here, we are going to take a set X, and this set X is precisely S with an element, and that is origin. We are including the singleton set X. From the concept of connectedness, it is clear that this set is connected, but what we can justify that this X is not path connected. In order to justify that this is not path connected, we will again show it by contradiction. It is to be noted that the set X which we have considered here is precisely the S whose graph is here, plus we are including only one element there, that is this origin. Now let us assume that this X is path connected. So we are assuming that this X is path connected. Again, it is to be mentioned here that the topology is the relative topology on X. Now, if this is path connected, what will happen? For all elements X and Y in X, there will exist a continuous function P from this closed interval 0, 1 to X, with the condition that P0 is equal to X and P1 is equal to Y. What we will do that, in order to create the contradiction, let us choose two elements from X, and one natural choice is, why not let us take this origin, that is 0, 0, and the second element which we are choosing, that is 1 upon pi n 0. Note that both the elements are in X. For it, if we want to check, note that this is X is 1 upon pi. What about sine 1 upon X? That is nothing but sine pi. Sine pi is 0. So this is an element of X, and by our construction 0, 0 is already an element of X. Because we have assumed that this X is path connected, so by using the definition of path connectedness, there exists a continuous function. We are taking that continuous function again by this P. This is P from 0, 1 to X, such that P0 is this origin, and the value of P at 1 is nothing but 1 upon pi 0. Again, it is to be mentioned that this function is continuous. We have already studied the concept of projection maps. Let us take, this is the projection map from R2 to R, which is given by pi 1 xy is equal to x. We know that this function is continuous. Now, if this function is continuous, we can talk about the composition of these two functions. That is, this is from closed interval 0, 1 to x, and from x to r. Even we can talk about the restricted function with respect to this projection function, but we are denoting this itself by this pi 1, and which will always be continuous. This function is continuous from our construction. So what will happen? Their composition, this pi 1 composition p is also a continuous function. It is to be noted that if we are computing the value of this function at 0, that is nothing but pi 1 of this p0. Note that p0 is origin, that is pi 1 of this 0 0, that will always be 0. Also, if we are computing the value of this composition at 1, that is nothing but pi 1 p1. It is to be noted that p1 is 1 by pi 0, so this will nothing but 1 upon pi. So what exactly we have done? We have constructed a function, and this function is the composition of this projection function and the function for defining path, that is p. This function is from closed interval 0 1 to set of real numbers with pi 1 composition p at 0 is nothing but 0, and pi 1 composition p at 1 is 1 upon pi. Because this function is continuous, now we can use the well-known intermediate value theorem. So if we are using intermediate value theorem, so by intermediate value theorem, what we can do, we are using this well-known theorem which we have also studied. If we are taking any element in between 0 and 1 upon pi, so the choice of this point is important. What we are going to choose here, we are choosing the elements of this form. This is 2n plus half pi. Why we are choosing the points of this form? It is to be noted that if we are finding out the value of sine 1 upon x, then this will be nothing but sine 2n plus half pi, that is sine pi by 2, and that will always be 1. Meaning is that we are choosing the points on which this peak is 1, that is the function is attaining this value, and this will help us to create or to see that there is some contradiction. Now if we are taking any point in between 0 and 1 upon pi, then by using this theorem, there exists xn in this closed interval 0 1 such that this pi 1 composition p of xn is nothing but this is 1 upon 2n plus half pi. From here we can conclude that, or we can think that, what about p of xn? It is to be noted that p of xn is nothing but 1 upon 2n plus half pi with 1, because sine 1 upon x at this point will always be 1. Also, we can conclude that this pxn, this is a sequence in x, and if this is sequence in x, whether this is converging, answer is yes, this sequence is converging. Note that this is converging to 0, so this pxn is a convergent sequence, and this sequence is converging to 0 1. Also, we have taken xn in this closed interval 0 1. So what we can see that this xn is a sequence in this closed interval 0 1. Note that xn is a sequence in a closed interval 0, 1. We can use the concept of analysis here by using the well-known Bolzano-Weierstrass theorem. We can conclude that there exists a subsequence. Let us assume that xnk, and note that this is not only a subsequence of sequence xn, this is also convergent. Now, if this sequence is convergent, assume that it converges to, let us take an element x naught. Question is, if this sequence is convergent to this x naught, whether x naught belongs to this closed interval 0, 1? Answer is yes. This belongs to this closed interval because this is a closed set. Now, if this xnk is converging to x naught by using the continuity of the function p, what about this one? Pxn should converge to px naught. Also, it is to be noted here that this x naught belongs to this closed interval 0, 1. What about this px naught? This belongs to x because of the definition of this p. Now, from here, what we have already seen that the sequence this pxn is converging to an element 0, 1 of R2. So, from here, what we can deduce that as pxn is converging to this element, that is 0, 1, and this belongs to R2, and xnk, which is a subsequence of xn. So, if we are talking about the convergence of this subsequence pxnk, this will also converge to this element, that is 0, 1 in R2. It is to be noted here that this element 0, 1 is not an element of x. At the same time, if xnk is converging to x naught, xnk will converge to px naught, and in this case px naught is an element of x. So this is a contradiction. Even it can be justified that this p x naught is nothing but this point in x. Thus, our assumption, that is the space x, which we have assumed that this space is path connected, is wrong, and hence this space is not path connected. So what exactly we have seen here? We have constructed an example, and this is an example of a space which is connected but not path connected. These are the references. That's all from this lecture. Thank you.